Micron just made the most advanced DRAM ever produced in the United States. But this breakthrough has nothing to do with your personal computer or gaming rig. The real stakes are whether we can finally build autonomous systems that make split-second decisions without relying on a cloud connection, and why the silicon currently being manufactured might be too expensive for you, but essential for survival in high-stakes environments. By the end of this analysis, you will understand how shifting memory architecture from raw speed to deterministic reliability is fundamentally rewriting the rules of edge autonomy in defense and industrial automation. For years, the narrative around semiconductor manufacturing has been dominated by consumer demand. We assumed that every new node meant faster frame rates for video games or quicker boot times for laptops. That assumption was a comfortable illusion because it ignored where the actual bottlenecks were forming. The memory wall is no longer just about how fast data moves. It is about whether systems can sustain consistent performance over decades of operation in conditions where failure is not an option. Micron's new 1-alpha DDR4 production line at their Virginia facility represents a critical pivot away from that consumer narrative toward something far more demanding and technically precise. Here is the thing you need to understand first. Memory has grown to nearly 2/3 of AI chip component costs, yet most discussions about this shift focus entirely on processor speed or neural network architecture. This oversight misses the fundamental hardware constraint that determines whether an autonomous agent can actually function in the real world. When a drone flies through a storm or a robot navigates a collapsing building, it cannot afford to wait for data to travel back and forth from a server farm. It needs local memory capable of handling massive state caching without introducing latency jitter. The 1-alpha node delivers exactly that by prioritizing density and reliability over the volatile performance spikes favored in consumer markets. Let us trace how this specific manufacturing milestone changes what is physically possible for edge devices. Previously, manufacturers had to rely on imported components or generic DDR4 chips designed with a tolerance for occasional errors because they were built for desktops where a reboot solves everything. In defense and aerospace, that volatility is unacceptable. A single memory bit flip during a critical control loop can be catastrophic. By moving 1-alpha production exclusively to domestic U.S. facilities, Micron eliminates the supply chain latency and geopolitical risk that previously forced edge deployments to rely on imported components with uncertain quality assurances. This creates a new baseline for viability in regulated sectors where long lifecycle reliability is non-negotiable. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the specific performance characteristics of this 1-alpha node compared to standard consumer memory. The primary value here is not raw bandwidth numbers you might see on a spec sheet, but the ability to sustain deterministic low-latency access over extended periods. This capability enables real-time control loops that were previously limited by unpredictable memory jitter. When an industrial robot arm needs to adjust its grip based on sensor fusion data in milliseconds, it requires a memory subsystem that behaves identically every single time under load. The 1-alpha architecture achieves this by optimizing yield and cost for high-volume specialized applications, rather than the low-margin consumer market where price sensitivity drives design choices. This shift effectively reallocates silicon away from the DIY PC market to create a supply dynamic where enterprise and AI contracts take precedence, leaving consumer builds as the last to eat in terms of access to cutting-edge nodes. The trade-off is clear. While this domestic scaling secures the supply chain for high-stakes applications, it coincides with the decline of the crucial consumer brand performance tier and rising prices for enthusiasts who previously relied on these chips for upgrades. However, there remains a necessary skepticism regarding its direct utility for PC users because few current applications can seamlessly transition between DDR4 and DDR5 standards without significant architectural changes to their software stack. The most profound implication emerges when we look at how this density transforms the behavior of edge autonomy itself. Current data lacks specific benchmark results quantifying exact latency improvements, but the strategic direction is undeniable. The technology enables breaking the memory wall by providing sufficient density to run complex AI models locally on constrained hardware without requiring constant cloud connectivity. This shifts system behavior from reactive data processing to proactive real-time decision-making. Imagine a sensor fusion unit that can cache terabytes of environmental state instantly and query it with sub-millisecond latency, allowing an autonomous vehicle to predict pedestrian movement before the event fully unfolds rather than reacting after detection. This architectural pivot means future edge autonomy will rely on industrial-grade memory architectures that prioritize reliability over consumer price points because the cost of failure in these systems dwarfs any savings from cheaper components. The transition signals a clear industry direction where hardware is designed for specific AI inference workloads and sensor fusion at the edge, optimizing every nanosecond of access time to ensure deterministic outcomes. While enthusiasts may face higher costs or slower adoption cycles as production lines focus on defense contracts, this reallocation secures the physical foundation required for machines that must operate independently in hostile environments. The gap between strategic announcements and tangible performance gains remains a point of friction until specific benchmarks are released showing how these new memory densities translate to actual edge behaviors. We know from industry analysis that memory now constitutes nearly two-thirds of chip costs, yet we lack the granular data on exactly how much faster an inference engine runs with 1 alpha density versus standard DDR4 in real-world scenarios. This uncertainty is a natural part of manufacturing transitions where yield ramping and software stack optimization lag behind hardware availability. However, the fundamental capability to sustain deterministic access without cloud dependency marks a definitive qualitative leap from fast to instantaneous decision-making. As we move forward, the distinction between consumer-grade volatility and industrial-grade determinism will only become more pronounced in how engineers design autonomous systems. The ability to break the memory wall locally means that complex AI models can run on hardware where weight and power are constrained, fundamentally changing what is possible for field-deployed robotics. This is not just a speed bump, it is a redefinition of the boundary between local computation and cloud dependency. By securing domestic supply chains for these specialized components, we ensure that critical infrastructure remains resilient against external shocks, while enabling machines to think faster than ever before without waiting for permission from a server farm halfway across the world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.